Alright guys, this lesson is going to be a continuation of our unit on biochemistry in anatomy and physiology. So what we're going to focus on in this particular lesson is molecules, compounds, and chemical reactions, and really talking about how it is that atoms bond together in order to create larger molecules and compounds. So it's important for us to indicate and remember that not all elements are going to exist in pure form. What we're talking about is being just pure elements. For example, hydrogen will exist in its pure form. However, it's much more common for you to find hydrogen in other compounds. So we're going to distinguish between a molecule versus a compound, and understanding that a molecule is just simply two or more atoms combined. So we're not really distinguishing whether they're the same atom, whether they're different atoms. So we're talking about hydrogen molecules, we're talking about water molecules, we can talk about a glucose molecule. All right, we're really just talking about two or more atoms combined together. So here we've got 2 atoms, here we've got 3 atoms, and here we're looking at 24 different atoms. Versus a compound. In a compound, what we're really looking at is that it has to be different elements combined. So what we need to notice here is that in examples, water can be a compound and glucose can be a compound. But we can no longer look at a hydrogen molecule as being an example of a compound, because it needs to be different elements, and pure hydrogen is not 2 or more different elements combined. So it's important for us to recognize that basically what we're saying is that molecules can be compounds, but not all compounds can be molecules. So it's important for us to recognize that they're distinctive from the elements that they're composed of. What we're saying there is meaning that hydrogen alone has different properties than a water molecule, and that water molecule is going to have different properties than that glucose molecule, and that's really because of what it is that they're bonded together with and how those atoms are bonded together. So molecules and compounds are also going to have definite types and definite numbers of atoms. For example, glucose is always going to be C6H12O6 when we figure it out. You're never going to have a different ratio of carbons, hydrogens, and oxygens to give you glucose. It's a definite number with definite types. So that molecular formula, like we were talking about, or like I was just demonstrating, a molecular formula is going to be exactly what I've been drawing on these previous slides. All right, molecular formula giving you the number and the type of atoms. So you need to indicate that it's going to be composed of carbon and hydrogen, and exactly how many. So when we look at methane, all right, when we talk about bonding, all right, we can recognize that we have different atoms that are going to take on different properties and be more or less likely to react. It says there that atoms with the outermost electron shells filled are stable and chemically inactive or inert. What we're talking about are these elements right here, which we refer to as the noble gases. Noble gases can exist on their own and aren't going to be bonding with anything else. They are inert. However, other atoms are going to be more likely to react with different atoms within the periodic table. So when the outermost shell of electrons is not completely filled, that's when bonding is going to take place. So what we're really looking at, what we're really paying attention to with bonding, is the outermost electron shell. Still bearing with me, guys, that my handwriting with this new tablet is pretty rough. So when we're looking at that outermost electron shell and we look at hydrogen, hydrogen only has this one orbital, or this one shell, that's looking to be filled. And in the first shell, what you're looking for is 2 electrons. So we're missing something in that middle space, or in that extra space. So hydrogen is looking to bond with something to fill that missing spot. Helium, however, has 2 electrons in its outermost shell, because helium is one of those inner noble gases, so its first shell is full. It has 2 electrons. Versus lithium, lithium has 2 in its first shell, but then it's got a third in its second shell. And its second shell here is looking for 8 electrons. Well, so is it going to be easier for lithium to lose that 1 electron, or is it going to be easiest for lithium to gain 7 more? Well, it's obviously going to be easier for it to lose that electron and forget gaining 7 more. So that's really determining how it's going to bond and react. One of our types of bonding that we're going to cover is ionic bonding. And what happens is that in ionic bonding, what we're really looking at is that opposites are going to attract. So we're going to have positives and negatives, that cation being our positive, anion being our negative, and it's ionic bonding, which means it's going to be bonding between ions, between charged atoms. And what happens is that it's kind of almost 2 steps. So in step 1, what's going to happen is that the atom is going to lose or gain an electron. Then the ions will attract. The ions that result will attract. So what I mean by that is that here we have a sodium atom and a chlorine atom. Sodium's first shell has 2, which means it's full, so we're good. Its second shell has 1, 2, 3, 4, 5, 6, 7, 8, which means that we're good. But sodium is atomic number 11, which means 2 plus 8 only gives us 10. We have that 11th electron in a third shell. So we've got 1 floating in a third orbital. Chlorine being 17, all right, chlorine is atomic number 17. Oops, that's a 7, guys. 17 means that we've got 2 in the first, we've got 8 in our second, which gives us 10, and then we only have 7 in our third, which means we're missing 1. So sodium is ready to give away that extra. Chlorine is looking to take an extra instead of trying to get rid of 7. So sodium will transfer 1 of its electrons to the chlorine atom. And as a result, sodium gives up an electron, which means it's going to have 11 protons, like it says here. And it used to have 11 electrons, but it gave away 1, which means now it only has 10 electrons. So 11 protons, 10 electrons gives us that positive charge. And chlorine has 17 protons, and it gained that extra electron. So it used to have 17 electrons, but now it's got 18 electrons, which means it's got 17 positives, 18 negatives, which is going to give it a negative charge. So now we have 2 ions. We've got a sodium ion and we have a chlorine ion. And what's going to happen there is we're going to go up to that step 2. The ions will attract. Opposites are going to attract to one another. So they're going to draw together, and what we're going to get is sodium chloride. We're going to have NaCl. Covalent bonding is another type of bonding that we're going to discuss. And in covalent bonding, what actually happens is that electrons simply get shared. All right, so there's no 2-step process of transferring electrons between atoms first. They're simply going to share because one of them isn't looking to gain or lose electrons any more so than the other. So here we have 2 hydrogen atoms, each having 1 and looking for an extra electron to fill that first shell with 2. Well, neither of them is more likely to gain or lose since they're the same thing, so they simply come together and share that 1 that each of the atoms has, that 1 electron. So ultimately, they become shared. So what you have here is an example that hydrogen atoms, all right, so in covalent bonding, hydrogens will form single bonds, and it doesn't necessarily mean between hydrogens. For example, carbon can bond with the hydrogen, and in that case, the hydrogen only forms 1 bond. But if you look down at the 4th bullet, carbon forms 4 bonds. 1, 2, 3, 4 off of the carbon. Down here, 1, 2, 3, 4 off of the carbon. Nitrogen wants to bond 3 times, and oxygen is looking to bond twice. So in the example of H2O, our hydrogen has 1 bond coming off of it, but our oxygen has 2 bonds coming off of it. So in covalent bonding, certain atoms are going to be more likely to form certain numbers of bonds so that sharing can occur. Hydrogen bonding is another type of bonding we want to talk about, and it's really talking about an attractive force. Right? I don't even necessarily want you guys to focus on it necessarily being bonding. What we're looking at is that attraction that exists between molecules. It's not actually a chemical bond that's going to form within a molecule. So we have a whole entire water molecule, and these hydrogens and oxygens are chemically bonded to one another, but between each of the water molecules, they have this attractive force. And that's really having to do with the fact that the hydrogens have a positive end and the oxygens have a negative end, so negative versus the positive, and we know that opposites are going to attract. So they have this attractive force, and that hydrogen bonding between water molecules is what we talk about being responsible for cohesion and adhesion of water. How water molecules are likely to cling to one another and to other substances is because these different molecules have charges based on the electron distribution within the molecule itself. So most of your electrons are going to be focused around this oxygen, where the hydrogen is not going to be really left with anything because its electron is sitting really close to the oxygen to be able to bond. So this outer end becomes positive and draws it towards negative molecules. In addition to being responsible for some of the properties of water, hydrogen bonding also comes into play with proteins and nucleic acids, and we'll talk a little bit more about that later. So focusing on that polar molecules that's responsible for hydrogen bonding, right, that slightly negative and slightly positive end that we were talking about is because of the distribution of the electrons in covalent bonding. So as you can see here, this is that water molecule. We've got 1, 2, all right, electrons in the oxygen, and oxygen has 8 electrons in it. So it's got 1, 2, 3, 4, 5, 6, 7, 8, which belong to the oxygen, and then those last 2 are shared with hydrogen. But because the electrons are drawn closer to the oxygen overall has more negative charges near it, while the hydrogens have more positive charges near them. So that oxygen becomes slightly negative, and these hydrogens are going to become slightly positive. So what we're really talking about is that distribution of the electrons. Structural formulas, so remember we talked about molecular formulas being the type of atom and the number of how many. A structural formula actually is a picture, all right? It gives you a visual representation of how those atoms are bonded together, not just talking about how many of them are. So here we've got those molecular formulas that I was talking about, and then the structural formula shows how. So knowing that in H2 it's 1 bond versus in O2 it's a double bond that bonds them together. In CO2, 2 double bonds, and